thanks everybody for attending this presentation. This is a presentation that we're making as part of the AI-ITMS deployment program in Delaware. And the modeling work that we're doing is just a small piece of this program. We just completed year one, so we've made some progress with the models. Again, we have a few more years left to go in this program. Hopefully, we'll get to have more results and more information as we progress this project. Next slide. So we're going to give an overview of the program itself and then talk specifically about the methodology, the modeling methodology, the data collection, and the modeling process itself. What are the challenges and what we plan to accomplish in the next couple of years under this program, specifically for simulation modeling. Next. So this whole project is part of the ATC MTD grant that DelDOT received way back in 2019. They have a lot of infrastructure in place in the state. One unique thing about DelDOT is actually they pretty much control all the different transportation elements in their state, like from transit to signals to freeways. Everything is managed under one entity. So it was kind of convenient for them to kind of try to integrate everything together using artificial intelligence and machine learning to benefit traffic operations. So they wanted to kind of do some test sites, demonstrate the benefits of a program that could look at all the sensor data, signal timing data, and combine machine learning algorithms to predict, at least in the near term, what's going to happen and how we can mitigate the impacts of things like events, congestion, special events, incidents, things like that. Next slide. So what is the scope of simulation for this project? So we had selected 3 different kind of mini case studies within this project. Like one is focusing on an urban area near Newark, which is going to look at things like recurring congestion, traffic, AM and PM peak periods, things like that, regular congestion-related issues. We had a rural area, which is in the Delaware Beach area in Sussex County, which is going to more focus on things like special events and the surge in traffic, especially during summer, where there's a lot of beach activity, weekend traffic. So those kind of situations. And there is another section which is we're calling it the CAV testbed. That is going to focus more. I mean, there is not a whole lot of congestion here. It's mostly in between 2 different destinations. But the focus on this section is going to be more on CAV deployment and how we get the information from the CAVs to assess performance, and also things like incident management, because there's only there is a freeway and a parallel arterial signalized corridor. So if there is any issue on the freeway, vehicles have to divert to the parallel arterial, and so the interaction between those 2 facilities is of interest to us. Next slide. So I'm going to hand back to Zelan to cover the modeling specifics and aspects of it. So Zelan, go ahead.
Sure. Thank you, Shankar. The project area includes the Route 1 and Route 13 corridors from Route 299 in Odyssey and Route 10 to Delaware. Route 1 is also named as Korean War Veterans Memorial Highway. This is a toll road across south and northbound in Delaware. So this is the toll road all the way here, and the parallel intersection Zelan intersection corridor is you have 13 here. And the 2 corridors are all about 29 miles long. The study area also includes the minor arterials to capture the impacts of congestions on southbound and northbound on the corridors. There are 5 emergency gates along Route 1, which will be used as emergency access points when the incident happens on the corridor. So 3 on southbound and 2 on northbound. And there are total 57 signalized and emergency gates in sections on Route 13. So this is the screenshot and aerial view for one of the emergency access points. This diagram workflow shows our process, the methodology from data processing to the final traffic incidents and congestion management. We have multiple data sources, including the Delaware Electronics real-time 24 hours data, which include volume, OD, speed, and travel time. And we also have Delaware.traffic count study for volume and speed peak hours, and also the Cube TDM models, which we will use this model to validate volume for other data sources. After we have all the data we need, we use spreadsheets to do the volume balancing for both freeway and arterial for AM and PM peak periods. We have three models here: synchro model, Zoom model, and the Whistle model. With the balanced network volume, we use this as the input to the Zoom network and run the ODME process to generate the OD tables which for the network. With both signal information and Zoom OD table, we can generate volume inputs, routings, vehicle compositions in Visum, which make the model ready for simulation runs. After the calibration for the base models, we did several traffic incident scenario tests. So data collection is one of the key process in this project because we have multiple data sources, but there are discrepancies and none of them can cover all the study area. Delaware detection data provides continuous traffic volume by corridor detections for 24 hours aggregated into 1 minute intervals. The detection data was collected from March 10 this year to March 23rd this year. Travel time and travel speed on corridor road segments were also collected from the same data set in the same date periods. Delaware traffic count studies were used as intersection turning movements volume as raw data. The data collected time of all study varied between October 2014 to March 2020. So there's a huge discrepancy in data collection date and also data collection peak hours. This is the screenshot from Delaware Transportation Management Center. They have all the detection locations marked in their Google Map-based review. And the Peninsula model is the Cube TDM model we used. It is a traditional four-step travel demand model. Year 2019 base scenario was used as a traffic directional volume and a vehicle composition data source. The model was used as supplemental data and a verification reference in this project. Even though we have multiple data sources, we still cannot cover all the intersections of freeway corridor segments. Some assumptions and reasonable interpretation would be conducted based on the collected data to fill the missing data gap in this project. So there are many challenges we have in our data processing process. Real-time data extraction is one of the challenges. This is the screenshot of the JSON file provided by Delaware Transportation Management Center. The electronic data is a real-time data. They don't have a mechanism or a database to save offline data. That means when we need data, we need to run the real-time script to manually drag the data down from the website. The data will refresh every 1 minute. So the team will run script for days to save the traffic data into the Circle database. Traffic volume balancing is also quite challenging. We need to figure out the missing TMC data gap since we only have 48 out of 57 intersections that we need in the traffic turning movement counts. Based on the Delaware electronics and detection volume data, we generated the hourly directional volume diagram for 24 hours pattern, and it shows the AM and PM peak hour based on the trends. So this chart shows the 24-hour volume trends. The green line shows the total network volume for the 24 hours. We can see there are two peaks in these trends, one in AM from 6:30 to 9:30, 1 in PM from 3 to 6. So we choose this as our peak periods. And you can see from the diagram that PM volume is about 50% more than the AM total volume. This diagram shows our workflow, how we deal with the TMC data processing. Turning movements count discrepancy in collected data. There are also missing movements and missing intersections. So we created this TMC data processing flow to interpret the volume for AM, PM, midday, and off-peak. We have this available traffic study count for 48 intersections, and we also have some available volume from the synchro. With this 48 intersections volume, we combine the 24 hours detection trends, and we sum up the AM and PM volume with the pattern of midday and off-peak. So we get a final intersection 20 movement count for AM, PM, midday, and off-peak. Within these 48 intersections, we chose several key controlling points based on their geometry and functions, and most of them are the main intersections in the urban area, and we interpret the other 4 intersections. So in total, we have 52 intersections out of 57 intersections with the turning movements count. With every data ready, we came to the traffic modeling part. We use the Zoom to generate regional OD pattern with ODM process. Our goal is to develop RAM-to-RAM OD tables. So we separated the freeway and arterial into 2 different models. Here is the screenshots of the Zoom model. This is freeway network, and this is arterial network. So the freeway is row 1, and arterial is UM13. With the new OD table, we use tools to post-processing WISM input to get by time intervals, 15 minutes time intervals, and study routings for RAM-to-RAM OD tables and visual composition for all the inputs. And by then we have the WISM-based model. There are 3 alternative tests will be simulated. So base AM and PM peak periods traffic operations were done with calibration. And we also did 3 incidence management tests so far, and we will show the results later. The special events will also be tested in the next stage, because there is a music festival in the downtown Delaware every summer. So there is a need to simulate special events for their model. This chart shows the RAM-to-RAM routings in the regional OD pattern, which we developed in Zoom. Let's take a row 1 southbound routing as an example. So vehicles will start from row 1 southbound starting points and all the way driving along the route 1 corridor. And it will choose exit 104 here. So the freeway routing ends here. After this endpoint, new arterial routing will start. Vehicles will follow the static routing. There are multiple routings here to go to the arterial endpoints. The RAM-to-RAM routing is more realistic than the relay routings, and it's not as difficult as end-to-end routings in Zoom ODME process, since ODME process may be a little bit difficult to converge, and RAM-to-RAM routing is easy to simulate congestion pattern too. So with all the volume-related inputs and the WISM network ready, we use WISM 11 to run the simulation for peak hours. We choose 6:30 to 9:30 as AM peak and 3 to 6 as PM peak, with 1 hour sitting time and 3 hour simulation time. The model will calibrate it in 3 steps: capacity calibration, system performance calibration, and visual review calibration. WISM model parameters were adjusted to meet the criteria of the throughput volume. These candidates model parameters include driving behavior parameter, lane change distance for different facilities. Travel time and speed profiles from WISM to compare with field condition were also used. Delaware Webtronic data was used as the travel time field condition criteria. And for the visual review calibration, we did several comparisons with the Google map. So here is the comparison charts for the VISM results and the Google Map results. VISM results was depicted in VISM using density per lane, and the Google Map typical traffic was chosen in weekdays in the peak hours. Comparing with these two, we can see that the VISM results almost match the field condition. Because of this special year, even though in the peak hour, it is not really congested in the fields. So besides the visual comparison, we also have some results for the travel time. This page shows the cumulative travel time for both Route 1 and your 13 corridors for both southbound and northbound. We use electronic detection data travel time as the calibration criteria for the model travel time calibration. So let's take the Route 1 southbound AM as an example. This curve, the x-axis shows the distance from 0 to the end of the corridor, and the y-axis is the travel time. We use the cumulative travel time to show the dots here. The line with blue and green shows the 10% more or less of the average field travel time, and the red line shows the cumulative VISM travel time. We can see from the charts that the VISM cumulative travel time lies between the two field travel time. We can say that based on the travel time, the model is calibrated, and it is same for the other corridors, directions, and peak hours. After we have the base VISM model, we also did 3 incidence tests using emergency gates at new Discovery Road. So the testing segment is in the middle of the network between new Discovery Road emergency gate and off-ramp to US 13 exit 119A. And this is the aerial photo of the emergency gates. People can use these gates to bypass the freeway. We did 3 scenario tests, one with 1 lane open here and no exit open, and one with section closed with the emergency gate open. And the third one is 1 lane closed, but with the emergency open as bypass. 1 hour was simulated from 4 to 5, which means from 3 to 4, the gate, there's no incidents happen. Only 4 to 5, there will be an incident happen. And PM model was chosen because it has a higher volume. So here is a more detailed description of the incident scenario. For the first one, we close 1 lane between these segments, and the vehicle still can use these freeways. For the second section closed one, we close this section depicted as gray. The vehicle will use this emergency gates and use the 2 local routes. One is green and one is red. And if there's a vehicle going to this local, they just continue using these arterials. And the third one is a combination of previous 2. 1 lane closed and a vehicle using these 2 routings to go back to the freeways. Here are the results for the Route 1. The heat map here is comparing the 4 scenarios. Vehicles will going from left to right as the southbound and time from 3 to 6. The tested section is between the red dots. We can see from the base model, there is no incidents and no congestion at all. All vehicles will run as green. So in green, we means vehicles run much higher than 60 miles per hour. If it is red, it means the vehicle speed is lower and lower. For the 1 lane closure alternative, we can see with the incidents happen, queues begin to back up until the lane reopen again and queues disappear very quickly, but there is still a little bit short wait for the downstream. And for the section closure one, we can see there's no vehicles coming from this section. And the queues build back up very, very fast. And even after the section reopened, the queue still going back to the south starting point of the Route 1 routing. And the third alternative is the best option we have. There's a queue backup, but disappears very fast. This is the travel time of results for the raw one. We can see it is showing the same result as the heat map. There's a little bit congestion and travel time increase for the one lane closure. And for the section closure, the travel time increased from about 5 minutes to 25 minutes, which is huge congestion all the way the corridor. And the third option is the best one. It almost by a little bit smaller than the 1%, 10% average of the field time. So this is besides influence on the freeway, there's also influence for the arterials. We choose two intersections example, 116 and 117. Our study segments is from here to here, and this is the end of the segments. Vehicles going from freeway to arterials and going back to freeway will use these left turns, and some of them will go through as shown before. Comparing with false scenarios, we can see there is a huge influence on the local intersections comparing with alternative 1 and alternative 3 because we divert some vehicles to the local. So for intersections 117, there's a huge delay on southbound for both throughput and left turn. We did some signal optimization for signals 117 because if we close this section, we don't have any volumes going from the westbound. So we can see from this table, the delay for 117 for alternative 2 doesn't look that bad, but for 116 it is, since vehicles will back up till this, until this intersection. There are many challenges we face during this program, and we will face the new one. One of the biggest one is how can we connect to the real-time data? Both includes the signal and the volume. What kind of the pre-process we need to do when we connect the real-time data? And we also need to develop COM and real-time API to connect the Delaware database too. And for the next step, we will use a dynamic simulating reason for 24-hour model and use COM to interface with real-time database. And several scenarios will also be tested. There will be 10 incidents management tests, including the vehicles using the emergency gates or using the ramps. And 2 special events will also be tested in the Delaware urban area. That is all for our presentation.
Excellent. Thank you both. Make sure everybody's unmuted here from your side. Yes, you are. Perfect. All right. Thanks, Zelan. Thanks, Shankar. For your presentation, let's go ahead and look at the questions. You are, yep, okay. I was like, making sure you're done, right? Okay, switch the slide. Okay, question 1, did you use a dynamic ODME or a static regular ODME? And if you did the static, how did you configure it for each 15-minute interval?
So we use static ODME. We didn't do the 15 minutes interval for Zoom. We only do that for Visum. So for Zoom, we only use 1 hour peak hour volume to do the ODME.
Okay. Thank you. Next question is, when performing the roadway closures, did you reroute the traffic directly in VSIM, or did you also perform the closure in Zoom and then re-export the assignment?
We did it directly in VSIM doing the routings. We did some partial routings and add some static routings and manipulate with the inputs too.
Okay. Those were the 2 questions that came in. Let's see if some more are flowing. I think that's it. You guys, maybe you can speak about your signal, oh, sorry. What assignment method are you using in the Zoom? What assignment method are you currently using in the Zoom?
Tiflo fuzzy, we use Tiflo fuzzy.
Use a Tiflo fuzzy, very good. Okay, and I think that I'm just looking at the stream of questions. I think that's it. Well, thank you both very much for your presentation.